surface on a major high volume pavement and really keep it in good functional condition if we have enough structure. There are various hot and cold surface recycling techniques that can be used that can remove some of the top surface, rejuvenate it in a way, and relay it. I will say with the hot in place techniques, they can be very effective, but they do consume a lot of energy. And then there's also white topping options in which thin bonded concrete overlays can be put on top of asphalt pavements. When we look at some of these treatments, you'll notice that things like those thinner HMA overlays or heavy chip seals, you'll see a higher energy use and higher greenhouse gas than some of the lower intensity applications like fog seals or slurries. But at the same time, life is almost inversely proportional to this energy and greenhouse gas production. And so things like fog seals will have a very short life, whereas HMA overlays can have a very long life. And so you really have to look at over the life cycle the best approach. Moving to concrete, there's this whole kind of tiered system as we do concrete pavement restoration. Many techniques are available. Not all projects will need every technique. Very, very common things that are done to restore ride quality can be partial depth repairs or full depth repairs where you have a failure at a joint, for example. A technique that lately has become, continues to become very popular is Dalbar retrofitting, in which load transfer has been lost. It's a way, if we address the underlying causes of faulting, for example, it could be a drainage issue, could be other issues, but where we can restore load transfer through the insertion of Dalbars and then follow up with something like diamond grinding. So when we look at kind of grinding that surface, once we repair the rest of the defects, we can hit it really with a new surface, very similar to that finishing of a hardwood floor. And within diamond grinding, what we find is a significant reduction in roughness, improved skid resistance, and reduced noise level with the addition of no additional material. And so this is, from a concrete perspective, really quite a good technique. Also, we have different surfaces available. There's conventional diamond grinding, and there's also next generation grinding, which actually can significantly reduce the noise levels even more. And so really, in conclusion, when we look at preservation, it's broadly believed, and research that's been done has shown that preservation is inherently a very sustainable practice. We can keep good pavements in good condition, smooth pavements smooth, quiet pavements quiet, and safe pavements safe through very low amounts of new material being used, little to none, and very little disruption to traffic. There are multiple options that exist. They continue to grow, I think. There's a lot of innovation that's occurring in preservation right now. And so it's actually, as far as pavements go, it's a pretty exciting area to be looking at. So you need to do your homework. Sustainability impacts on low volume roadways, as mentioned, are very closely correlated with agency costs. And so as agencies balance their budgets, they're really applying a sustainable solution to low volume roads generally. What we find is because of the very heavy influence of user cost on higher volume pavements, there's a deviation with agency cost. And so therefore, greater integration needs to really occur for high volume roads to really, I think, maximize the benefit of preservation from a sustainability perspective. And so I believe that is quite possibly my last slide. And so now hopefully, Kurt, we'll turn it over to Ahmad.
Yes, very good. Thank you, Tom. We appreciate that overview on pavement preservation techniques and treatments and how they can affect sustainability. And I would like to remind everyone that you can submit a question anytime using the chat box feature, and we'll be sure to compile those and address those at the end. So we now want to move from pavement preservation and pavement maintenance types of considerations to those that come into play at the end of life. And to lead us into that discussion, we have Dr. Ahmad Al-Qadi. Ahmad?
Thanks, Kurt. Good afternoon, everyone, and good morning to the people in the West. Let me make sure that I get control of, here we go. So as you can see in this figure here, for the pavement life cycle, inputs, which is including various types of energy and raw materials, and outputs, which means the emissions to air, land, and water, result from the consumptions of energy and raw material sources. And that's will be in the 5 phases of the pavement life cycle as shown in this figure. As you already know that these 5 phases are the production of pavement materials, the construction of pavements, the use of the pavements during its service life, which we always refer to as the use phase, and finally at the end of the pavement's life. When the pavement reaches its end of life, it can be recycled, allowed to remain in place, and reused as part of the supporting structure for a new pavement, or of course removed from wrap place and recycled and put back. Or the second case here is removed and landfilled. Each of these 2 activities has an economic and cost and environmental impact, such as the consumption of raw materials, energy input, as well as emission, which should be considered as we are discussing the end-of-life phase. As quality aggregate sources are depleted, there is a growing importance given to incorporating recycled and industrial byproducts materials even more aggressively in new and rehabilitated pavements. Therefore, the pavement end of life is defined as the final disposition and subsequent reuse, processing, or recycling of any portion of a pavement system that has reached an end of its useful life. And that can be done either on-site or off-site recycled operation. It can be reused in pavements, in new pavement layers such as overlays, or it can be through the landfill operation. So for both asphalt and concrete, we have 3 end-of-life options. For asphalt concrete, the first options is to remove the asphalt concrete pavement to a central plant, and there it will be further processed, and this further processing, it will be done in order to replace the virgin materials in the subsequent application. And that's what we usually use for hot or cold center plant. Then we can use it also on-site as part of the full depth reclamation, which I'm going to be talking about this later on today, and recycle it as putting it as an AC layer for a new pavement application. We can use it also as we can also dispose it in a landfill after millet, remove it, and transport it to the landfill site. For concrete, similarly, we can recycle the concrete pavement and remove it, crush it off-site or on-site, or we may sometimes do a rubblization. We can reuse this by keep it in place and use it as part of a supporting structure, and then overlay it with either asphalt concrete or Portland cement concrete as the white topping. And of course, the same, we can break it, remove it, and transport it to a landfill site. An ideal goal would be to use recycled material to produce a long-lived, well-performing pavement, and then at the end of its life be able to use those materials into a new pavement, effectively achieving a zero waste highway construction stream. This would not only produce distinct cost advantages, but it would also provide significant reduction in the energy consumption as well as the emissions, and would eliminate the need for a landfill disposal. So if you look here for the asphalt concrete recycling statistics, for that, I think it's the recycled pavement can be reused either as a pavement base layer or included in a surface layer. In addition, we can use this for embankment, fills, and scores of other potential uses. According to recent industry data, it has been shown that less than 1% of recycled pavement was sent to landfills. So for asphalt concrete in particular here, the total RAB used as reported, I think in 2013, was 68.3 million tons, which is really significant. So if you look at the figure in front of you here, you can see that most of the asphalt concrete has been used as recycled in hot mix asphalt or warm mix asphalt, and good portion has been used in aggregate. Of course, we are using it now as a black rocks in concrete too, and there is just a small amount that it has been used for other places. And again, it's just less than 1% used in landfills. On the other hand, for the concrete pavements, the total amount of recycled concrete is estimated to be around 140 million tons. These recycled pavement materials can be used back in new asphalt or concrete mixtures, or used as aggregate in base layers, or even in a number of other uses such as fill, riprap, and ballast, as you are shown here in the figure, in according with the CDRA data in 2014. So using pavement materials at the end of its life is accepted as one of the most effective ways to improve pavement sustainability. However, a comprehensive economic and environmental analysis for recycling and reusing pavement materials must be done in order to fully quantify the effects of the various end-of-life options. Major contributing end-of-life unit processes are the landfill, recycling operations, as well as transportation. For example, pavement recycling is highly affected by material transportation cost as compared to the cost of a new virgin materials delivered to the construction site. Hazardous waste in construction and demolition waste landfills comprise a small percentage of the recycled or the materials that is generated from pavements. Therefore, the long-term environmental impacts of landfill resulting from pavement recycling materials is insignificant. It has to be noted here that recycling processes include removal, transportation, crushing, screening, and stockpiling. So we have different options that they are available for recycling asphalt and concrete pavement materials. However, in order to assess realistic benefits for recycling, the whole recycling options or all recycling options and their associated costs should be evaluated. The important factors that contribute to the cost of pavement recycling and environmental implications are technology or the available technology, disposal cost, transportation, application, as well as the quality of the recycled materials. So the available technology can be an important driving cost determinant for on-site and off-site recycling. If the pavement is recycled in a central plant, the environmental costs include demolition at the job site, of course, crushing, screening, and stockpiling at the plant. On the other hand, the construction equipment used for on-site recycling, including cold-in-place recycling, hot-in-place recycling, rubblization, and full-depth reclamination. In the recycled pavement materials if we have the recycled pavement materials disposed at a landfill, the total disposal costs usually include the demolition, the landfill tipping fees, and the transportation, which includes trip distance and what kind of mode we are using, such as a truck, trail, ships, and so on. The land tipping fee, actually, it can range quite a bit. It can be from $10 to as high as $70 per ton. But a very important consideration for landfill disposal is the diminishing number of the landfills that they are available for us to dump our pavements that we're planning to put it in a landfill. The original The quality of recycled pavements, its process, storage, and local specification, it's always determine its final application, as I mentioned earlier. It can be reused in pavement layers, embankments, fills, as well as other potential applications. The quality requirements for using recycled pavements can be different for asphalt and concrete pavements, including surface and base layers. The potential contamination risk that we may have in the recycled pavements can also limit its use and application. So no doubt that there is an increasing interest in the notion of what we refer to as closed loop or zero waste thinking, which will promote standardization of the recycling process. And of course, this will improve the overall sustainability as well as the overall quality of pavements. In our approach to develop a strategy for optimizing the use of recycling options, assessments considering all environmental and cost determinants are needed. Hence, all the four concepts of sustainability assessment should be applied, and that's include the functional performance, which means here that the pavement or resultant pavement should be equal or better than the existing pavements or what we were planning to do without the recycled materials when it comes to performance. From an economic point of view, the life cycle cost, it should be better than if we are using regular materials. Otherwise, I think it will not make sense for people, or there will be no incentives for people to use it. And third, the life cycle assessment should show that there is a positive environmental impact, and adding to that the sustainability rating that we are getting from this. So it's critical in a closed loop pavement or zero waste pavement system to quantify and measure the benefits to incentivize contractors as well as owners. Some of the relevant questions that need to be addressed to generate robust, realistic, and scalable assessment of pavement recycling include how much environmental credit or burden should be given to recycled materials, which is here, what is the environmental impact of recycled materials we're planning to use? Who's going to bear the burden or enjoy the benefits? Is that the initial producer or the last producer or user of the recycled content? Where should these credits be counted? How should transportation be counted in any model that it's used for this? Which life cycle stage should be assigned to? So LCA deals with these issues through allocation rules. Allocation is defined by ISO 14044, which is as partitioning the input or output flows of a process or a product system between the product system and one or more product systems. So there is several allocation rules and procedures which are applicable for the recycling materials. So using set of rules for recycling pavement materials allow defining whether upstream or downstream procedure should receive recycling credits. By the way, ISO 14044 defines a closed loop as being when a material from a product is recycled back into the same product system, while defining the open loop as being when a material from one product system is recycled into a different product system. So the most commonly used allocation methods for pavements are the cutoff and the substitution methods. In the cutoff method, all benefits of recycling are given to using recycled materials. So the life of recycled materials starts at milling of the old pavement, followed by transportation to a depository place for processing and transportation to a job site in order to be reused. All benefits are given to the pavement using the recycled materials by reduction in the use of virgin materials without any priori knowledge about the rate of recycling at the end of its life. The substitution method, on the other hand,